I'm Rob Torpy. I'm a senior manager at Deloitte. I work within the AI and data space. I'm I don't know if double hokey if it's per each degree, but I do have 2 degrees from tech, one in communication studies and one in BIT DSS. So a little bit of both the liberal arts and the business tech side. I just wanted to express some appreciation again for our planning committee, Luke, Megan, and Bradley, to bring all this together. It is the inaugural Day for Data, so look out. Next year will be bigger, better, expanded. So appreciate everybody's attendance and engagement today. One thing I wanted to note is, as a part of my role on the Executive Advisory Board for Center for Business Analytics, Deloitte is actually the founding sponsor of the Center for Business Analytics. So this is just another way that helps us, engage, bring thought leadership down to tech, and if you have feedback on any of this, please reach out to me during the networking events. And of course, if you have questions about Deloitte, happy to answer those as well. So I know we're between you and lunch. So it's a little bit of an envious position, but I do want to introduce my colleague, Eric Christensen. He is a triple hokey, if I'm counting. So degree in math and physics, and then a PhD in physics. So he's actually the technical lead for the Deloitte FutureScape digital simulation platform, which he'll, of course, go through more details on that today. But as a high level, the FutureScape team has conceived, developed, and delivered solutions to high-priority customer missions surrounding infrastructure, transportation, finance, and logistics. So another way to say simulation, this is a digital twin platform. You may have heard that in the market. So Eric is an eminent expert in distributed computing and machine learning, and I hope you enjoy his session today. So I'll welcome Eric.
Okay, that works. Hey everyone, thank you for inviting me to come on give this talk. So like Guidehouse, I'm from the consulting arm of Deloitte. We do a lot of different analytics, but I'm really going to focus in on what my team does, which is centered around simulation. Hopefully it's something that's a little bit new as a topic for a lot of you, and I'm just really going to try to deep dive into that aspect of it. So starting out at data, it's becoming easier and cheaper to collect lots and lots of data. And as we've heard about from other speakers today, that helps bring in insights about the current everyday operations from center level details at the edge, all the way through some of the more macroscopic properties like user retention or things of the sort. But it also opens up possibilities for doing advanced analytics. So techniques like machine learning and simulation allow you to look at not only what's going on right now, but forecasting forward. What do we understand about today that can help us figure out what's going to happen in the future? And that's going to be the major driving point. And helping clients, they might run into these 2 extremes of data. On one side, they have too much data, essentially. They have a high velocity coming in, so just trying to analyze the amount that's coming in is cumbersome and challenging. Or they have a situation where they're trying to find like a needle in the haystack, where they just have petabytes of data to try to crunch through. It becomes very hard, and they built out entire technologies centered around this sort of problem space. On the other side of this dichotomy is where you have little to no data. This might be a situation where you had something that's just dangerous, so it's hard to create circumstances where you can collect data on it. Maybe it's just really expensive to gather, or maybe it's about a circumstance that's never really happened before. Various businesses and people making key decisions still are faced with trying to make an informed decision about those sorts of circumstances. So wouldn't it be nice to be able to give some sort of quantitative insight and help drive that decision-making process. This is where simulation enters into play. So the idea with simulation is that we take some real-world system and try to distill it down into some digital twin or here I wrote digital replica that encapsulates really the core features of the real-world system, but in a space where you can start probing it in different ways. Maybe you want to add something new. Maybe you want to change a property about it. Or maybe you want to just run a whole lot of different circumstances and try to find out whether there's some rare event that occurs. And really, what does that do to our overall outcomes? And so by creating this space, you can really just search around and try to understand everything about that system without having to have it happen before. Now, my team focuses on something that we call agent-based simulations. And in these, the agent is the fundamental building block. You try to define all the various properties that you have about them. So here I have an example of a car where you might store information like what's its position, its velocity, acceleration. You can see, as a physicist, why this might appeal to me. The charge, fuel level, which lane is it driving in, what route it's going to follow along, who's driving in it. All these sorts of things are properties of the agent that we want to track, and typically you choose things that let you know about outcomes that you need to make decisions about. I'll get into some examples here in a little bit, but the agents have these state variables, and they have models to decide how those state variables change. Now, I said that the clients might have a situation where they have little to no data. That's really just about some circumstance that they want to understand. Even in these simulations, it's very data hungry. What drives all these is these interactions either with itself, with other agents, or with the environment. And all these come from maybe other machine learning models that tell you, what happens when things interact in this sort of way, or from scientific studies. All these enter in, and they are both data hungry in creating the models, and then also data hungry in actually creating the overall environment that these live within. So it never leaves. You always have to be informed and grounded. And then the other interesting thing about agent-based models is that everything is built from the ground up. So because we're defining the individual properties of these agents, how they're interacting, everything that occurs within the system is some byproduct of those choices. We like to call this emergent behavior, where you didn't pre-specify how something was going to behave, but because of those interactions, you discover something that's a property of the overall system, built up from the fundamentals. So I have a little picture here. Like, you don't want to say, like, this section of road is going to be congested. You'd rather want to say, well, if people are trying to get from here to there, and these are the options available to them, does it become congested? That way, you can change properties of it and discover, is it impacted by those changes? Nice property of those sorts of models. So our team, we kind of broke this down into 4 steps, a little arbitrary, but it's all right. Step 1, we build out the environment. So what's the system look like that these are going to move around in? The second step is about deciding what agents are we going to have within that world, and what properties are they going to contain and how they interact. And then once we have those established for the particular circumstance we have at play, what sort of computational environment do we actually need to fulfill this? And I'll get into that in a lot of detail, because that's where our team really shines and where we've made a differentiator amongst ourselves. And once you've set everything up, you're able to run it. What actually happened? Trying to get insights from that simulation. There's a lot of different ways, but we try to turn those what-if questions into something actionable. And all this is cyclical, and I'll talk about that a little bit more. So starting out with preparing your environment, it all depends on what it is that you actually want to simulate, but things that we've done in the past, we'll bring in information about, say, like road networks. I have a transportation-heavy focus for my team, but Could be for lots of stuff. Road networks, buildings, where cell towers are, if you need to know how people are connecting to cell towers, like power infrastructure, traffic lights, things of the sort. A lot of this stuff is pretty much static. It exists predefined throughout the entire simulation. It's not really the things that are interacting, although agents might interact with them. So we can pull those in either from data sources, or it could be generated. There's actually been circumstances where we've had to create synthetic, fabricated situations to either make something more reasonable to deal with in the environment that we're in, so like make it like unclassified or things of the sort, or it just doesn't have the data that exists for it. So you might need to say, like, let's assume that we understand how these things might be created. Let's make a similar process to spontaneously create like a road network or a power grid. Okay, so we have the environment. We define all the different agents that we have within it. Doesn't have to be one type of agent. Could be lots of different things. So one particular simulation that we had worked on had agents that were representing so cars, traffic lights, the power nodes, we'll call them, within a power grid, telecom towers. All these different things had their own individual behaviors and their own interactions that we had to define and create a way for them to communicate with one another and change their state. And a lot of interesting physics goes into that, which is pretty cool. And then I'm going to spend a little bit of time on this side, but there's potentially an issue of scale that comes in with really any sort of computational problem. There's a limiting factor on how big can you make this simulation, or you want to crunch more data. How do you do that efficiently? And so one way is to distribute it, have multiple computers working on the problem together. And there's two kind of major approaches there, and we've done both of them within our team. One of them is that you want to go wide. This is a circumstance where you might have simulations that have a lot of variance in them. So as you run one of these and you run them again, you'll get drastically different outcomes potentially because randomness and stochasticity in the model causes different outcomes to occur, and they cascade, and there's long-reaching ramifications for it. And so by that sort of necessity, you need to run it many, many times and look at the distribution of outcomes. And another reason why you might want to do that is that there's just a lot of different things you want to test. So maybe there's a particular question you have in mind, but it could take a wide range of variables, or multi-dimensional. And so scanning over that space might require you just to run a lot of different simulations in parallel. And these all can be fairly independent. They don't need to communicate with one another, so it's really nice. And you just kind of deal with the fact that you have just lots of data coming out at the end. Cloud computing makes this quite easy nowadays. You don't have to limit yourself to what you have on premises. Now, the other side of this is where you have a simulation that's just so big it doesn't all fit within memory. So one computer can't really run it by itself. And so our team has differentiated itself on this sort of task by, we've created patented technology that we use internally that distributes the whole thing up so that multiple computers handle different sections of the world. It doesn't necessarily need to be geographical, but a lot of the times it is. And they all compute what's going on in their section, and then they share that information where there's a shared boundary to another computer. And so we can do this sort of lockstep thing where everybody computes what the next step is going to be, and then they share that information and then synchronize and then move on. And so we're able to go to like really, really big, massive scale simulations this way. And it provides a lot of interesting questions for how to actually implement this and stuff like that. I think there could be a whole class just on ways of actually creating agents that handle that sort of distribution. But it's neat. And then once we have that overall simulation, it's able to run from end to end and communicate and finish. We start asking the what if questions. So sometimes it's not necessarily clear what it is that you want to find out about it until you look at the outcomes. You know, maybe something happens in this that you weren't expecting to happen at all, because you're defining this from the fundamental interactions. So, you know, what happens when a whole lot of these all come together? It's not always clear, but usually I'll say that we go in with some question in mind. You know, what happens if we add a new transit line or something like that, and then analyze the data. So where there was no data before, this simulation acts as that source of data. You know, we're working on creating a simulation that's going to produce petabytes of data just from one. So it's, you know, potentially immense with the amount that you have to analyze, but it doesn't need to be. So the simulation itself, throughout it's running, it's producing outputs, and those can all be analyzed the same way you would with any sort of data analytics project. And you know, you gain the insight the same way you would from there. And then, you know, once you have these sorts of insights, it brings about new questions. You know, working with the client, they might spot something that they see, and then they'll want to say, well, I'm noticing that, you know, this isn't helping our clientele in this sort of region. Why is that? Is there something we could change about what we asked in the first place to try to drive that change going forward? And let's run that through instead. And it might require you to make changes to the underlying assumptions you built into the model, or you know, the way that you handle various aspects of it. But this whole thing is very, very cyclical. You'll find that in really any sort of consulting work, I think. So we've done a lot with our simulation platform, and these are just some projects that I've worked on. I've mentioned one of them already, this city resiliency, where we're modeling different infrastructure layers, having them connect to one another, and trying to understand if we were to you know, change a property, like turn off this power node, what's the cascading consequences it has in the region. So in this case, it was like, you know, turns off like traffic lights and some cell towers, but it also had some, you know, non-immediate consequences of like overloading some of the adjacent cell network, and like which ones were picking up most of the slack and things like that. We worked on financial networks where we modeled lender, creditor, I can remember the terms, relationships where we'd step through quarter by quarter and look at how finances changed for that particular institution. These entities are all institutions. They could potentially go bankrupt, and you know, what's the cascading, you know, consequences of their failure there. A heavy one that we're doing still currently is about transportation. We're simulating, you know, millions and millions of people all making decisions about their, you know, daily life, and can we drive the needle on different aspects of that? And then finally, this one I'm still working on right now as well. It's about supply and logistics. So we created a fully synthetic world, you know, multiple continents, looking at how vehicles, as they're traveling across and doing their operations, they have like needs for fuel, needs for food and water, et cetera. How different technologies that we want to potentially implement in the future have an impact on the overall performance of that network. So lots of, you know, variety of use cases that all you know, benefit from this capability of looking and testing something in a situation that has happened. I'm going to, you know, double click, I guess, on the transportation use case. Don't know how detailed I'm going to get into this particular slide, but I want to go into a little bit of like the structure of how one of these simulations, you know, looks, and go from there. And it's just easier to talk about the traffic one than any of the other ones. So all these simulations have some set of inputs that drive the overall construction of the environment and the agents within it. And so in this case, we'll read in the road network and transit network, usually directly from the client. So the clients that we've been working with are trying to predict something that's like 20 years out. They have plans that take a while to implement. They're billions of dollars of infrastructure and change. And it just doesn't really matter what's going on right now as much as what they expect it to look like in the future. And so we'll use what their expected road network and transit schedules are going to look like. We also have some synthetic trip lists. These are what a person within the simulation, usually informed by surveys or from ad tech, like cellular device collection, what sort of activities are they going to do? So, this person lives here, they're going to go and drop off the kid and go to work and so on. And so you create this schedule that they follow for that particular day. And you see it in, and then we have the overall population that has demographic information synthetically created, and there's lots of different ways of doing that. And these are informed by surveys and data, but using machine learning to generate the actual schedules here. And then all this enters into the sort of simulation loop where you see, all right, for this particular time step, who is it that is actually going to go on a trip right now? Let's decide, all right, for this person, they're going to go from here to there. What are all the different routes they could potentially take? So they could be driving on tolls or like HOV by themselves. They could be taking active modes like walking, biking. They could be taking transit, so they could walk to transit, park and ride, et cetera. So we compute all the different paths that they could potentially take for that option. Very compute intensive, as you might imagine. And give them those choices and say, all right, which of these would you most likely take? These feed into something that's essentially like a mode selector that weighs these based on conditions related to the demographics of the person. So how old are they? Can they even drive a car in the first place? Their income and stuff for price sensitivity, as well as things about the route, like how long it is, how long it's going to take, how much it's going to cost. And they'll make a decision on that. And this is all fed in from things that are regional specific. And then once they've chosen a mode, we assign them to the network and let them carry along their day, interacting with other people on the roads, getting on the buses, et cetera. And they'll move, and it will take out information related to congestion and feed that back into the path finding. And so this whole thing just keeps stepping, like second by second. Let's move people along the road network and compute. And all the while that this is going on, we're just taking data out. What are the properties of the road network while they're driving on it? How many people took this particular transit line? What is the decision-making process that led this particular individual to take this mode of transportation? And exporting those all out for analysis at the end. And we've been able to answer questions for a variety of clients now reusing this procedure that we've created. Because we've centered around just the individual traveler, we can answer questions about equity. So if someone's proposing a new change to the system, is it actually affecting the people that need it most? So we can follow along and say, what's the distribution of ethnicities that this impacted, the income that it impacted, et cetera. And we were able to use this specifically at one of our clients. They did want to add potentially some new transit lines. They didn't know how much they wanted to price it out or who was it going to impact. And so we're able to do a study and say, let's run this a bunch of times, scanning from like $2 all the way up to $20. Which one is going to give you the most revenue? And so we're able to try to figure that out directly. And at that revenue, that price point, now who is it that's taking that line? So we can sample individuals from that collection. Maybe it's not the ones they wanted. Or we can look at the overall ensemble. So that's handy. And then The other sorts of questions we help a lot of clients answer are related to environmental impact. So, cars on the road isn't necessarily great for the environment. They have potential options they can enact for their plan for trying to drive people away from single occupancy vehicles mostly. So are people actually moving those modes and stuff? So because we're modeling that choice of mode selection, we're able to try to answer these sorts of questions. And so we're helping a different client out. They had a variety of different options available to them. They wanted to test them in different combinations and figure out which of these combinations would help us actually substantially reduce the greenhouse gas emissions for the region. They have targets to reach. It's mandated. What's the best thing here? So we were testing lots of new transit lines that were sweeping across the area. Trying to make them run more frequently, or adding micromobility. So there was a whole structure about getting changes to housing density and structure to try to move people in closer, and then having a micromobility service that helped them navigate around and get to those transit networks. Having a stick also by increasing tolling or the cost it has to drive along those roads. And we're able to test, which of these options actually does help with VMT, or vehicle miles traveled, converting into greenhouse gas emission. Very useful, helpful with billions of dollars of decision making there, and not just for transportation. And having worked on this, I've been on the team now for 5 years, and seen it grow from just a handful of people to all the way up to like about 20 or so. Learned some lessons along the way. And this first one is applicable to everything, not just simulation, really just like any data analytics. The data is really going to be the key thing here. Always question your assumptions about it. What you think this data is really telling you in the first place, or like how it was collected, might have happened differently than you thought, or there might have been some things baked into it. Always check to see, check for cleanliness, check for those assumptions, revisit it even after you've gone through the pipeline. So there's often times where it's hard to tell what to really be looking for in the data, what corruptions there might be lurking in there, but we'll see something really strange in the outputs. No one's taken this section of road. Why is that? Well, it turns out that there's two one-way roads that are like pointing against each other, and no one can take it. And so we're able to go through and try to figure out details about that, and it's always worth revisiting. The second major thing is that no matter how good you think you design something in the first place, someone's going to ask you to do something new with it. So always design it to be flexible and agile, so that when they most undoubtedly ask you for something new, you can replace it easily or modify it easily. It's been a useful technique. And then last thing, just generally for consulting, you're going to come up with answers, you're going to come up with things to be able to tell clients and people that are making decisions. Frame it in a way and help them find out answers that actually let them make better decisions. So they have a certain selection of levers available to them. What levers does what you found out translate into? Can we formulate this to help them choose from those levers? A model on its own is not useful at all. And there I'll open up for questions, otherwise I'll be hanging around.
So when you're there and you can construct like the geospatial analytics, do you tend to collaborate research with companies such as Garmin, Motorola, and Uber?
So our team has not explicitly modeled or worked with them. That particular example was tasked specifically with using open source data sets. So it was a unique circumstance where we really wanted to do it with as little input from external sources as possible. So that one's a little weird. In principle, yes, we would partner and try to work with groups that have good insights on the spaces that we need to model. There's a vast array of different examples that I gave there, and I'm definitely not an expert on any of them necessarily, because I'm a background in neutrino physics. It's all quite a bit different, but yeah.
First off, this is really awesome, great stuff. Kind of the consulting physics interaction, how do you convince a client when you have no data, low data, to say, believe my simulation and the results coming out of it, but I don't have anything to validate against real world yet to say, this is what you will get for sure.
Yeah. So generally, we like to build out a baseline scenario where we can test the assumptions that we build into the agents and the models that we have. So for any of the transportation cases, one thing that we've been fortunate enough with is that there's a federal mandate that they also have a regional model as well. But even in the lack of that, there's current data that we have about what it's like today. And so in that sort of circumstance, we would simulate conditions as they exist. There is potentially duplicative work and extra work to create a trip list for today's world versus the future world. But we would establish the baseline set in a circumstance where we can test against it and validate there first, and then make comparisons there. And in the circumstances we have to deal with something in the future, we like to, everything's very open about how those models behave and stuff like that with the client when we share that, and usually, grounded in papers or other research. But we'll also do ratios that really help test things without having to get everything's approximate, but trying to get the details of something, perfect. You can still get lots of good details about looking at ratios and how things change when you compare two of them. It's a trick we use in physics also, ratio like near versus far detectors and stuff like that. Yeah.
Thanks for the presentation. I have a question on the framework. So you have agents, you have directions in the model. So I think agents is a very common concept in the field of reinforcement learning. And I think my key problem with my question is how do you define interaction? Let's say you don't have the data, how do you decide a man will be likely to walk 5 miles a day, or how do you decide that?
Yeah, all those would have to be steeped in data. So the clients we worked with have regional information about how far they might travel, or they might use a rule of thumb estimate. It's not reasonable to ask people to walk more than a mile to get to transit or things like that. So they'll put in some cutoffs. They should be steeped in data with how they're created in the first place. You have to be creative and open in the circumstances where it's something that doesn't have a great model that exists currently. Some of the contested logistics work that I've been doing just hasn't really been studied at the scale. We're doing it at a global scale, and we have to make lots of approximations and assumptions about the behaviors there. And in those circumstances, it's just being really open with the client and making sure that they agree with those assumptions.
How do we simulate and optimize systems under uncertainty which is very layered, or where it is very layered, and you want to make sure that you get this and optimize that structure?
Yeah. So, big question. So optimizing, so there's, I'm assuming what you mean optimizing, you're saying I have potentially a big selection of options, let's find the best one. There's a lot of, what I would typically recommend is a black box solution essentially, where you treat the simulation as a function that takes inputs and gives you an output. you could do like Bayesian sort of statistics and say, let's vary these things and sample different points and then try to narrow in on spots. When it's something that's like super rare, as in like maybe it happens only at one specific value, it's tough to find without like a parameter sweep. If it's super rare in like physics, so that you just run it a ton of times until you can cover to like some error bar of like we should have seen it by now. Okay. Well, thank you all very much.